Hello, everyone, and welcome to the first live session of our 8-part webinar series, Seismic Design in Steel, presented by Rafael Sabelli. Today is September 10th, 2018. My name is Nate Goner with AISC, and I am your moderator for today's presentation. I would like to introduce the presenter and author of this webinar series, Rafael Sabelli. Mr. Sabelli is a principal and director of seismic design at Walter P. Moore in their San Francisco office. He is a recognized expert on seismic design of steel structures. His experience includes the design of new structures, retrofit of existing buildings, nonlinear seismic analysis, and the development of new structural systems. He participates in many national technical committees responsible for building code development, including several committees here at AISC. He has earned a Special Achievement Award from AISC as well as the T.R. Higgins Lectureship Award. Rafael, I want to thank you for being here, and I will now turn the floor over to you.
Thank you, Nate, and hello, everyone. It's my pleasure to present the live portion of this night school class, Seismic Design in Steel, Concepts and Examples. As you know, the overall objective for the course is to teach principles of seismic design and to show those principles applied to two common systems, the special moment frames and the buckling restrained braced frames. And in so doing, we will cover the requirements for the application of seismic design to those two systems. I think it's useful for me to offer to you some additional resources that you can turn to. The resources that I've identified for this class include the AISC Seismic Design Manual, which relates very closely to the design examples that I'm going to present. Ductile Design for Steel Structures, a textbook, primary authors Michel Bruneau and Chai-Ming Wang, and I also participated in the writing of this textbook. And then a free download from AISC, Steel Facts for Steel Buildings, number 3, Earthquakes and Seismic Design by Ron Hamburger. This covers some general information about earthquakes and how they affect buildings, and it's really a great resource that you can use to better understand some of the material covered in the first few sessions. Additionally, at the end of each session, I will identify one or two other resources that might prove useful. Other resources that you have available to you are the Steel Solution Center, which responds promptly and thoroughly to questions from AISC members. And also you can send emails to nightschool@aisc.org, questions specific to this seminar, and they will find their way to me, and I will answer them. So we've already covered, or you've already covered in the recorded portion of this class, some introductory concepts, including introduction to seismic design, general treatment of moment frames and braced frames, and the general treatment of the seismic design of buildings. Now we enter into the live part of the class, which is the application of these requirements to a specific example. In today's session, we will plan out the seismic design. Several things that can be done in advance of designing braced frame and moment frame members will be done, and we'll set up the load combinations and other things for the design. Then we'll proceed on to the next 3 classes where we'll perform the analysis and design the moment frames and braced frames. So let's proceed to planning the seismic design. In today's session, we will select the system. We will determine the seismic weights. We'll configure our frames. We'll determine our base shear for the system in each of the principal building axes. And we'll do a rough comparison of wind versus seismic so that we can proceed with the seismic design with a fair amount of confidence that we are selecting the members that will be essentially the final members in the design and that won't be governed by wind. We will also cover the determination of irregularities, both in general terms and specific to the building that we are designing. And then we'll construct the load combinations using the appropriate overstrength factor and redundancy factor and so on for the actual design. So we'll proceed to the building that we have. We are taking the building from the AISC Seismic Design Manual, fairly consistent with how it's laid out there. It's a 4-story building. We will use a special moment frame in one direction, and that is very similar to what's done in examples 4.3 and 4.4 of that Seismic Design Manual. In the other direction, we will use buckling restrained braced frames, which are covered in example 5.5. And then the diaphragm example, which is from section 8 of that manual. This is a typical floor layout. It has some openings. They don't affect the design too much, but when we get into diaphragms, we will count on the diaphragm that's there, considering the opening. In one direction, in the long direction, this is the elevation that we have. We have 30-foot bays, and typical floor heights are 12.5 feet with a 14-foot floor at the first floor. So 4 bays in this direction, 3 bays in the other direction. Also, the column splices are here above the second floor. In the short direction, the bays are 25 feet, not 30 feet. Continuing on, we select a location. This is a fake location, but it's somewhere with reasonably high seismicity. The soil type is type D, an office building, so it's risk category 2 with an importance factor of 1. Because it's only 4 stories, our allowable drift is 2.5% of the story height. But for purposes of the example, we'll keep it to 2% to make sure that the cladding doesn't see excessive demand. So that's something that is a design choice that can be done in coordination with the architect and other affected parties. So we're keeping this building a little bit stiffer than the code requires, but that's going to be easier on the cladding system. Speaking of the code, this is designed to IBC 2015, which uses ASCE 7 2010 for loading, AISE 360 for steel design, ACI 318 for concrete, and AWSD 1.1 for structural welding. Additionally, AISE 341 is required for the seismic design. As we'll see later, we're selecting systems that use AISE 341. And for the special moment frames, we can use AISE 358 to get the for a pre-qualified connection. And consistent with those, the use of AISE 341 and AISE 358, we're using the Seismic Welding Supplement AWS D1.8. So all of those things, you notice the years are not exactly current. There are more recent additions, but those haven't found their way, say, into the building codes of the various states. However, in a number of cases, I will be highlighting differences from the 2016 ASE standard compared to the 2010, or the 2016 AISC seismic standard compared to 2010. So those bright red highlights will be used to identify things that are slightly different in the newer editions of the code. All right, we have a floor load, a dead load of 85 pounds per square foot. This is the same that's used in the Seismic Design Manual. We have a roof load that's slightly less, but the seismic portion of that includes some roof partitions that are braced against the roof diaphragm, or some floor partitions that are braced against the roof diaphragm. And there's a floor live load of 50 pounds per square foot, and consistent with the seismic design manual, we're treating that as already reduced, and we're not going to get into detailed calculations of live load reduction. It's a snow load of 20 pounds per square foot, and then a curtain wall dead load that is 14 pounds per square foot times the story height. So that works out to be about 175 pounds per foot along the perimeter of the building at every level. So at this point, it's beneficial to determine our seismic accelerations. We have enough information to do that. We can turn to the USGS website. You can always look up USGS seismic accelerations and in Google or another search engine, and the correct web address will come up as the first or second search result. So this is what it pulls up, an online application where we can enter in our location and other information, and we'll get our corresponding seismic acceleration suitable for use with ASE 7. You'll see that if you're looking to use other standards, such as the 2016 ASE or ASE 41, there are links to those as well. But we're using ASE 7. So here we pull up 2010 ASE 7, that's the appropriate code. Then we give the site soil classification. We select the risk category because, amongst other things, the seismic design category is a function of the risk category. And then we put in the address. And this obviously is not a real address or a real zip code, but you can put in an address including zip code, and it will generally find the location of your building. You can also put in latitude and longitude down below here, latitude and longitude. You can determine those elsewhere. So you should confirm, regardless of your method, that you do have the right location, just to make sure there wasn't a typo. And once you're satisfied that all of this input information is correct, you compute the values. And the USGS website application gives you a spectrum for the maximum considered earthquake and for the design response spectrum. And that's typically what we look at in the code-based design. 2/3 of this maximum considered earthquake is the design response spectrum, and that's what we select our values from. I've just magnified the values given here to make them more legible. It gives you the 1 second and 0.2 second accelerations, essentially in bedrock. Then it incorporates a site factor for each of these, corresponding to the site class that you specified. And then it takes 2/3 of those values, and this is what we input into the code equations, SDS and SD1. ASE 7 2016, by the way, this is a fairly major change, is asking for a ground motion hazard analysis in many different applications. So if you're on site class D, rather than using default values, you end up essentially required to have a ground motion hazard analysis if the seismic acceleration is greater than 0.2 at 1 second. What essentially happens, though, is if you want to avoid doing the ground motion hazard analysis, you can assume that the building is a very short period building and extend that short period plateau out. And in this region here, you can take this equation, this period sensitive portion of the curve, and multiply by 1.5. So the modified spectrum, if you don't do a ground motion hazard analysis, looks something like this. So it's not really a penalty for a very short period structure, but if you have a structure, a period in the range of 1 to 2 seconds, it's a substantial penalty. So, or even beyond that, it's a substantial penalty. And the reason is when you do your ground motion hazard analysis, or have a seismologist geotechnical engineer do your ground motion hazard analysis, the spectrum will look perhaps something like this. It may be below this conservative assumption, but it won't be all the way down to what we've been using with ASE 7 2010. So that does represent a fairly big change in the 2016 edition of ASE 7. All right, let's proceed to system selection. We have systems that are limited by seismic design category. So the first step is to figure out what our seismic design category is. We have these two tables in ASE 7 in Chapter 11. There's a table that will give you seismic design category based on SDS, another table based on SD1. We have to check both of them. And then to check for risk category or for seismic design category E and F, we look at the S of 1 acceleration. So really 3 different checks that we're doing. So the first, we take the highest seismic design category based on those 3 tests. We'll start with this test. Our SDS is 1. So it's greater than 0.5. So there we are. This table is telling us that we would be in seismic design category D. We do the second test, this other table based on SD1, and we check whether SD1 is greater than 0.2, and yes, it's confirming seismic design category D. Now we're going to check to see if we're in E or F. S of 1 is not greater than 0.75, so we're not in seismic design category E. And of course, we're not risk category 4, so we're not in seismic design category F. So we've determined seismic design category D. Now we turn to table 12.2-1 in ASE 7. This is actually a digest of that that's printed in the seismic design manual. It's just the steel system, so it's a little bit more concise. But it's the same information that we have in ASE 7, table 12.2-1. So we start with our seismic design category. This is the relevant information. And we see that these 3 systems are just not permitted in our seismic design category. So we won't consider ordinary moment frames or this system, steel systems not specifically detailed for seismic resistance within R3. Those things are not permitted. Then there are a couple of more, or a few more here, that have a height limit of 35 feet. That's not realistic for what we're doing for a 4-story building. So we're going to eliminate those as well. So we're left with a choice of several different systems. We are choosing special moment frames and buckling restrained braced frames. We could have chosen other systems, but we'll choose those 2. So the other ones are permitted, but we're simply not using them. We're using the special moment frames and the buckling restrained braced frames. Special moment frames, no height limit. Buckling restrained braced frames, height limit of 160 feet. Both work for our structure. Okay, we need to specify materials that we'll be using in the design equations in the coming weeks. Beams, ASTM A992 with a yield strength of 50 KSI. We also have the RY factor that we'll be using to get expected strength of those elements. For the heavier sections that have a flange thickness greater than 1.5 inches, we have to specify a minimum Sharpie V-notch toughness. For the sections that have thinner flanges, we expect that they have that same level of toughness or a higher level of toughness, so we don't test those sections because it's essentially a waste of a waste of effort to test those thinner flange sections for V-notch toughness. Columns, same material. Again, with the Sharpie V-notch toughness testing as required by AISC 341. We also are permitted A913 grade 65 and in 2016 grade 70 for buckling restrained braced frame and special moment frame columns. Typical connections will use plate material, A36, yield of 36 KSI, A325 bolts, threads excluded. For the seismic system, these have to be pre-tensioned with a Class A fang surface or better. The base connections, we will use grade 50 plate. We'll need it because of the high loads at the base. Also, when we use that thicker plate, if it's greater than 2 inches, again, per AISC 341, we need to test it for minimum Sharpie V-notch toughness, 20 foot-pounds at 70 degrees. We will use anchor rods, grade 55 anchor rods that are weldable per supplement S1. So if you want weldable anchor rods, you have to specify supplement S1 for grade 55. Grade 36 anchor rods are always weldable, and the grade 105 are never weldable. But 55 can be weldable if you specify the supplement. All right, so that weldable material permits us to fix damaged or perhaps mislocated anchor rods. It gives us a lot of solutions to field problems. So I highly recommend that you use weldable anchor rods when it is possible. This is a standard fix for a too short anchor rod that can be extended by welding. In AISC Design Guide 1, there's a treatment of different types of problems that come up in the field with anchor rods and solutions, including this welding detail. All right, so welds will use 70 KSI material with a Sharpie V-notch toughness, 20 foot-pounds at 0 degrees, and where we have these demand critical welds that will come up in sessions L3 and L4, we need to specify 40 foot-pounds at 70 degrees. Those are welds where we expect inelastic strain. We also need to make sure that the lowest anticipated service temperature is either 50 degrees or higher, or if it's not, we need to specify a more strict Sharpie V-notch toughness requirement. So for our building, it's all in conditioned space, so we can assume the anticipated service temperature is greater than 50 degrees. All right, the buckling restrained braces, the core material that we'll use is A36, but we add some specific or some additional requirements to the A36. A36 gives us a minimum yield strength, but we like to be a little bit more limited in the expected yield strength, and this is something that's consistent with the buckling restrained brace manufacturers. So this would be this is not an actual data about yield strength, but it's a schematic diagram that shows a distribution of expected yield stress and the specified minimum of 36 KSI. So very rarely does a piece come in that doesn't meet 36 KSI, and that's, of course, rejected because it doesn't meet A36. For the buckling restrained braces, we put a larger minimum on that, 38 KSI, and we also put a maximum of 46 KSI. So you can see that there's some rejected material expected. A few pieces will come in between 36 and 38 KSI. Those do meet A36, but they aren't used because we have limited the range. And some pieces do come in above 46 KSI, and they are not used for the yielding core of the buckling restrained brace because we've specified a maximum of 46. By limiting this window, it permits us to be a little bit more precise in our design of both the brace and its connections. So we can design the brace as if it's yielding at 38 KSI and then design the connections using an expected strength that is on the order of 42 KSI. And that's consistent with how we use expected strengths in AISE 341. All right. For the buckling restrained braced frame, the connections use gusset plates that are 50 KSI, the very large forces that have to be developed. And the bolts that we're using are A490 grade, threads excluded. And the materials match what was tested by the manufacturer, as we'll discuss in session 4. That has to be confirmed once we're sure who the manufacturer is. Manufacturers often assist in connection design, either performing some calculations for review by the engineer of record or vice versa, doing their own parallel calculations, looking at making sure that the connections for their braces are adequate for the loads that they anticipate. Doors and roof, 2-inch deck, 3 1/4 inch lightweight topping, 4 KSI with number 3s at 12 each way. Normal weight concrete at the foundations, 4 KSI. All right, so those are the materials that we'll be using. There are some quality requirements. These are specified both in AISC 360 Chapter N, that's the main steel specification, Chapter N. There are some fabrication and erection quality control requirements. There's inspection, quality assurance. There are tables in AISC 360 Chapter N for welded and bolted joints and so on that give different tasks before, during, and after. For non-destructive testing, there are rates of frequency for each test. And there's also a program where there can be approved fabricators and erectors that if the authority having jurisdiction approves, quality control can be done in the shop and without a third-party quality assurance and inspector in parallel with the approved fabricators QC staff. So different jurisdictions have different approaches to this, but it is a possibility in many jurisdictions. AISC 341 Chapter J covers similar territory, but it's a bit more stringent for the seismic system. So there are additional requirements. So over and above what's required in Chapter N of 360, we have requirements in Chapter J of 341. These include requirements that demand critical welds. And AISC 358, the pre-qualified connection standard, if we're using one of those pre-qualified connections, has additional requirements, say for the reduced beam section, cut, and then AWS D1.1 Section 6 has quality requirements, and D1.8 Section 7 has quality requirements. So all of these things are required by our building code to make sure that the built structure can reliably behave as it's been assumed to behave in the analysis and design. All right, let's construct the effective seismic weight of our structure. We don't have significant storage, so we don't have to worry about that. The snow load is relatively light. It's less than 30 pounds per square foot, so we don't include that in the seismic weight. So the weight is going to be a function of our dead load and plan area and our perimeter. So here's the plan area that we have, the 4 bays of 30 feet plus a foot on each side, 3 bays of 25 feet, foot on each side, and the product of that is about 9,400 square feet. And the perimeter is about 400 feet. We multiply these times the dead load that we have. So here's the Here's the distributed dead load, and here's the cladding load. And that turns out to be 868 on a typical floor. Roof weight is a little below that because of the lower distributed weight. And so our total weight is about just over 3,300 kips. All right, now let's get into something that looks a little bit more like engineering design. This is our plan, as you'll recall. We're going to use moment frames in the long direction. Presumably for architectural reasons, we will have 3 bays of moment frame on grid line A and 3 bays of moment frame on grid line D. And then we'll use buckling restrained braced frames on grid lines 1 and 5. Here's an elevation of the moment frame. Seems perfectly fine. We have 3 bays, 4 stories tall. And for the buckling restrained braced frame, it looks like this, just 1 bay, 4 stories tall. You probably expect a fair amount of overturning in this configuration. The important decision early on with moment frames is to determine what the connection is. And the reason for this will come clear in this list. We're going to use the reduced beam section connection. So this is a pre-qualified connection that achieves very good rotation capacity by moving the plastic hinge away from the face of the column to a purposely weakened section in the beam here. So that weakened section will see a lot of inelastic strain, but that inelastic strain can be handled very well within the flange of the beam, much better than it can be handled, say, in the CJP weld there. So we're protecting that connection at the face of the column by weakening the beam slightly away from the column. So the section at the face of the column is stronger than the yielding portion. We verify this through so-called capacity design, where we take the capacity at the plastic hinge location and compute forces elsewhere consistent with achieving that capacity. There is a reduction in stiffness. If you remove part of the beam flange, the moment of inertia goes down, and that has an effect on drift. So this is important to account for in the analysis. If we ignored this effect and found ourselves right at the drift limit and then included the effect afterwards, we would be over the drift limit. So we set our drift limit at 2%. In order to meet that drift limit, then we have to use an effective stiffness for these beams that is consistent with the use of the RBS, or reduced beam section connection. Also, because of the narrower flange width in this region, there is a potential reduction in stability that has to be considered. Address that in session 3. For buckling restrained braces, we want to make sure that we're going to specify braces that are available. Core Brace is a major manufacturer. Nippon Steel has also done many buildings in the US, and there may be others. Braces in the range of, say, 100 kips to 1,000 kips. These have been used extensively in mid-rise, low-rise, and mid-rise projects, and they're readily available. When you get above 1,000 kips, the braces become, they're more special, and you should definitely verify that they are available and that testing covers the brace that you want to specify, because it is a tested system. The braces end up being stiffer than simply the minimum core area taken from work point to work point. And in our analysis, we need to consider that. Sometimes, depending on the period of the building, the stiffer it is, the shorter the period, and the higher the design base shear. So we may be sensitive to the stiffness assumption of the braces. We want to make a reasonable stiffness assumption. We'll be looking at manufacturer's literature in order to make sure our assumption is reasonable. We are using a chevron configuration. That's the upside down V. in a 30-foot bay frame. Actually, we have, we're using it in the 25-foot bay frame. The manufacturers do publish literature, and I found literature covering the 30-foot bay. So I could give the manufacturer a call. In fact, I will cover this in some detail in live session 4. But for preliminary purposes, I'm going to assume a factor of 1.4, assuming the 25-foot bay is pretty similar to the 30-foot bay. Okay, so I have my systems picked out. The moment frame will be reduced beam section, and the buckling restraint brace frame will be in the chevron configuration with that stiffening factor of 1.4. ASCE 7 gives me methods of determining an approximate period based on building height. That's T sub A. That's my structural height, almost 52 feet. ASCE 7 also allows us to use the analysis period, so we can construct a model and use that period. However, our model isn't allowed to be too flexible. Remember, the shorter the period, the higher the base shear. So ASCE 7 says, at least for determining base shear, your model can't be too much stiffer than this, or too much more flexible than the approximate period. So that's reflected by the CU factor. So if you're using your actual or your model period, you need to check against CU times TA. For an area of high seismicity, that CU factor is 1.4. So we're going to assume that we don't have a model yet. We could just use the approximate building period, but ultimately we will have a model. And based on experience, we know that the model is going to be more flexible than that approximate period. So we're going to make some assumptions now, and then maybe have to adjust our design later once we have the model and have the real period. Okay, so this is the approximate period from ASCE 7, or the special moment frame, about 0.66 seconds. We're going to assume that when we model it, it's going to be over CUTA, so that we will be governed by CUTA, so that maximum period that ASCE 7 will allow us for this height, for this structural height, is 0.92 seconds. We will use that to get our base shear. I will say that a special moment frame is very rarely governed by the design base shear and the strength requirements, and much more likely to be governed by the drift requirements, as we'll see in session 3. So the assumption of CUTA here is fine. It's not going to govern the design anyway. Buckling restraint braced frame might very well be governed by strength limits or strength requirements, especially for a 4-story building, which isn't very tall. The approximate building we get from, or the approximate period we get from ASCE 7 is 0.58 seconds. We're going to assume that our actual building period when we construct the model will be longer than this, but maybe not all the way to CUTA. So I'm going to assume 1.3. It's typically in that range. You know, it depends a little bit on the number of factors. If it were a hospital, it would probably be a shorter period than that. So that's the assumption that we'll make. We definitely need to verify this assumption later once we've constructed our model. So if we use 1.3 times T approximate, that gives us about 0.75 seconds. And we'll, at least for preliminary purposes, we'll construct a base shear based on that. So here's the moment diagram, or here's the moment frame with the base shear diagram. This is essentially the spectrum that you get from the ASCE 7 equations. The first equation here is the plateau of the spectrum, so that gives this portion of the spectrum. The second equation is period dependence, 1 over T, and then there are a couple of minima that kick in at longer periods. And there's also another region that isn't relevant for a 4-story building where it's over T squared. So the shape of this changes as you get out to longer periods. Okay, so putting in our information, there's the period that we've assumed at 1.4 CUTA, a period of 0.918 seconds, and that gives us a base shear of 0.818 times G, which is larger than either of these two minima and smaller than this maximum. So that's the base shear coefficient that we'll use for the special moment frame. We do the same thing for the buckling restrained braced frame. We get the same R factor, but a different period. And so we end up with a base shear coefficient of about 0.1 G. So we apply those with the building weight that we've already determined, and we get a base shear of 271 kips for the strength design of the moment frame, and a base shear of 331 kips for the strength design of the buckling restrained braced frame. So I mentioned earlier we like to do a wind versus seismic comparison. This is part of what I call effective design. We want to essentially, when we can, select the members for the governing load effect and then check the members later. So for other load effects. So if seismic governs, we'd like to pick out our beams and columns for the seismic load and then check for wind. If wind governs, we'd like to pick out our beams and columns for the wind loads and then check for seismic, including proportioning. This is intended to reduce the design work so that you're not designing twice. You're designing once and then verifying. In order to do this wind versus seismic comparison, we have to do a fairly a thoughtful comparison. We'll compare the strength requirements. We'll compare the stiffness requirements. And the stiffness requirements are a little funny because for wind, we're considering perhaps a serviceability load. And for seismic, we're considering a safety load, a collapse prevention type of approach where we are looking at the full seismic load and the expected seismic drift. So the seismic one is corresponds to a very rare earthquake, whereas the wind stiffness requirement essentially corresponds to perhaps a 10 or 25-year wind, depending on the client's expectations. For the strength design, in our location, we're using 115 miles per hour for our ultimate wind load, wind exposure category B, with a topographic factor of 1, and for risk category 2. I'm not showing any of this analysis, but here we go. We have forces in the X and Y direction, and I'm just showing case 1. There are other cases that need to be considered for wind, but I'm going to say case 1 is perhaps representative of the magnitude of the wind load. Okay, so I'm going to compare the base shear for both wind and seismic, the overturning, because the load distributions are different for wind and seismic. Seismic tends to be a little more top-heavy than wind, so more overturning for the same base shear. I'm going to do the comparison both in the moment frame direction. We have a different base shear for both the moment frame and braced frame. And we also have that's for seismic as well as wind. We have different base shears because we have different systems in seismic, and we have different base shears because we have different exposed area in wind, and we may even have different loading as well. So here are the base shears for wind and seismic. Seismic has much greater base shear and much greater overturning than wind, and that's true for both the braced frames and the moment frames. If the wind were a little bit higher, I would also say we need to compare the overturning with the overstrength load effect. We are required to consider that for seismic, for columns and seismic frames, and that might govern over wind even if the regular wind overturning governed over seismic. So you can see here that seismic is governing by rather a lot. So for this design, we definitely want to size everything for seismic loads and then verify that they meet the requirements for wind loads. And it may not need to be very detailed a wind analysis, maybe complete the wind loading analysis, but the level of comparison may not need to be more detailed than this for the primary lateral system. However, components and cladding may well be governed by wind, and that should not be neglected even in areas of very high seismicity. So if wind controls the base shear, you still need to check the story shear at every level because the seismic load is more top-heavy. Okay, so now we'll look at the effective stiffness requirements for this building. For serviceability, we're looking at a 10-year wind. So that's the typical shorthand that we use for establishing that is 0.7 times the 50-year wind pressures. ASE 7 2016 doesn't give the 50-year wind pressures anymore, but you can still get them either from ASE 7 2010 or other sources. And then the typical deflection limit that we use is H over 400, or a deflection of 0.0025 times the story height. Okay, so we'll compare the correct base shear and drift limit, and make sure that the stiffness requirement that we're using is going to be the governing stiffness requirement. The seismic drift, the base shear for drift in a seismic analysis is going to be different from the base shear that we use for the strength design. Since we're looking at a stiffness, it's actually the lower base shear that we want to use. So if we have a drift limit of 2% for seismic, and the shear that corresponds to that is 100 kips, but the design base shear is 200 kips. If we use the design base shear, we would be saying we have a much more lower stiffness requirement. So as we go through this, hopefully that will become very clear. So for the wind serviceability, we take the wind base shear, 0.7 times 176 kips divided by that drift limit, and that gives us essentially a stiffness requirement. In that same direction, our seismic stiffness requirement, looking at the drift limit of 0.02H for the deflection that's amplified by C sub D, we get a stiffness requirement that is roughly twice the wind stiffness requirement. So if we meet the seismic requirement for stiffness, if we meet the seismic drift limit, we will meet the wind serviceability requirement because the ratio is 1.7. It's pretty clear that seismic governs. In the east-west direction, it's similar. Our base shear is lower. And then for the special moment frame, again, the C sub D factor comes into it, and we have a factor of 2.7. So for this direction, if we meet the seismic drift limit, we're guessing that we'll meet the wind drift limit probably by a factor of 2.5 or so. We can verify this after we've designed our members, but at least we know that we're picking out our beams and columns in this moment frame using the appropriate load combination that's going to govern their selection, and then therefore our design will be a little bit more efficient in terms of engineering calculations. All right, let's take a few minutes to go through the irregularities. The purpose of going through these irregularities is to limit or is to make sure that we're using the appropriate analysis options. For some cases, we'll need to use a modal response spectrum analysis if we have the irregularity. They may affect our building layout. So if we have a building layout that just doesn't work, this irregularity check is going to identify that. So if we check for irregularities at the beginning, we can save ourselves rework later. Some irregularities emerge later in the design after we've done our analysis. So we're going to double check those in sessions 3 and 4 after we've selected members. But we will at least go through all of these irregularities now and make sure that we identify ones that we have to keep an eye out later. So we'll start with the horizontal irregularities. There's a torsional irregularity. We compare displacements at corners of the building in each direction, and we compute the average and compare the maximum to the average. And if the maximum is more than 120% of the average, that's an irregularity. And the reason we check this is buildings that are subject to a lot of twisting see a lot of damage. And we address this by amplifying the torsional moment, essentially requiring our buildings to have a lot of torsional strength. We also restrict highly torsional buildings in higher seismic design categories. There's an extreme torsional irregularity version of this, and that's just 1.4 instead of 1.2 as the threshold. So if we have that extreme irregularity, that means that we're delta 2 is more than 140% of the average there. When you have a complex layout, it's pretty easy to do. You can just draw a box around it. If you're doing X and Y analyses, draw a box that's aligned with the X and Y axes and pick the corners of that box for your irregularity checks. Doesn't matter if the building doesn't actually reach those corners, you'll get the same irregularity computation or that same torsional factor as if you used points that are on the building at the maximum of X and maximum of Y. Okay, so if you do have the torsional irregularity, you need to strengthen it. Our building is very regular, so even with offsetting the mass as we're required to do by 5%, that can't have an effect of more than 10% on that maximum displacement. So in neither direction can we have that torsional irregularity because we're essentially symmetrical and have our lateral system at the perimeter. If we were symmetrical and had our lateral system in the interior, the effect could be much larger than 10%, but at the exterior it's limited to 10%. So how do you control it? Well, you can move more of your resistance to the perimeter and you can stiffen up the perimeter frames. Next irregularity is the reentrant corner. Both of these bites have to be greater than 15%, or this one bite has to be greater than 15% of the building dimension in both directions. That creates a notch-like effect. We increase diaphragm forces and require dynamic analysis for taller buildings. We just have a pretty minor bite there, and so we're not going to trigger that reentrant corner irregularity. The best way to address this is to provide a pretty robust load path back into the body of the building, as shown here with those collectors, and also to not to have portions of the diaphragm cantilever out without some stiffness out there, at least not cantilever out too far. Large openings are also an irregularity. The area here has to be greater than 50% of the gross area to trigger the irregularity. Again, we have a notch-like effect where that occurs. We have a small opening, nowhere near 50%, so we don't trigger the irregularity. Similar to the other irregularity, we want to provide a pretty robust load path around this, same as if it was an opening in a beam web. Another horizontal irregularity is when the lateral system offsets horizontally out of plane. Really all the code tells us is make sure we follow that load path using the amplified seismic load in the diaphragm. We have the same layout on each of our stories, so we don't have an autoplane offset. It's not triggered. There's a non-parallel system irregularity. This is just cluing you in to the fact that analyzing this sort of layout in an X and Y direction won't get you the maximum load on those skewed moment frames. So all it tells us to do is to make sure that we do an appropriate analysis to get the maximum force on those skewed moment frames. You can do an X and Y analysis and do the square root of the sum of the squares on the forces in that moment frame, or you can do an analysis with the base shear applied in the direction of that moment frame. Obviously, we do not have skewed systems in our layout here. So the horizontal irregularities, torsional irregularity, we're pretty sure is not present or likely. We'll check that in the end. And none of the other irregularities do we need to check. Vertical irregularities now, a soft story. What we do is we compare the effective stiffness of one story compared to the story above. That effective stiffness is the shear divided by the displacement. For a multi-story system, that's going to be a function of the load distribution. So what I always tell engineers is just use whatever load distribution you're using for design. Say it could be the equivalent lateral force procedure. Get your displacements and your shears and calculate an effective stiffness based on that. If you are less than 70% of the stiffness of the story above, or less than 80% of the average stiffness of the 3 stories above, then you've got a problem. You've got the irregularity, and the code tells you to do a dynamic analysis. Dynamic analysis may not give you very different forces, but it will at least pick up on this effect and the fact that this mode is a dominant mode. All right, and then there's the extreme version, and simply the factors are changed, and it's not allowed in some cases. Soft story, it's pretty easy to use the ELF and just use the load distribution from the ELF to get that effective stiffness. Modal response spectrum analysis, a little more it's a little more nuanced. You still can use the effective story shear and story drift. I find it pretty simple to use the ELF, though, for this check. All right. We're going to proportion our members to the demand. We don't think a soft story is going to be likely, but we don't know enough at this point, so we're going to have to check it later. Mass irregularity, there can be a dynamic effect. If we have a huge mass in the middle of the building, greater than, say, 150% of adjacent stories. So we do a dynamic analysis and we pick up on that effect. We look at our story forces or our story masses, story weights, and it's clear that we don't have that 150% bump. So we don't have that irregularity. There's a geometric irregularity. That geometric irregularity is a change in the length of the lateral system. This is kind of a holdover irregularity. It's really, it was there before we had stiffness and other similar checks. So if you have this irregularity, you're also likely to have, say, a story stiffness irregularity or something similar. Nevertheless, this irregularity persists in the code. If we have a change in length more than 130%, we need to address this irregularity, make sure that we have the load path for both the horizontal load to be dragged out and the overturning load to be carried down. We require a dynamic analysis to pick up on any dynamic effects. Clearly, our frames are pretty regular and there's no in-plane irregularity, so we don't have to worry about that any further. In-plane offset is somewhat similar. We require amplified forces for the overturning, which are required for all of our special systems anyway, and we require amplified load for the transfer of that horizontal force to the frame in plane. Very similar to the out-of-plane offset, but this one is in plane, and so it's considered a vertical irregularity rather than a horizontal irregularity. But clearly you could you see the similarity to the out-of-plane offset. The only difference is this is load in a strut or a collector rather than shear load in the diaphragm. And we don't have any of those offsets. Finally, we have a weak story irregularity. We look at the story shear strength and compare that to the level above. If we are less than 80%, we have a problem. We have a weak story irregularity. We could have a concentration of story drift and damage in that level. We require a dynamic analysis for this. I'm not sure a dynamic analysis really fixes it, but we do prohibit a weak story in certain uses, say in higher seismic design categories E and F, which is good. If you do have a weak story, I think the best thing to do is to make it stronger. And then the extreme weak story, it's just a different ratio. So how do you get that story shear strength? It's pretty easy calculation for a braced frame. We can just take the brace capacity and take the horizontal component of it, do that at every story. Moment frames, maybe a bit more nuanced. There's a decent example we're putting in the new seismic design manual that's going to be published very soon this fall. That strength can be constructed using a portal frame type of analysis that we did in the recorded session 2. We can calculate the shear at each column using the probable moment at each beam, amplified by the full length divided by the length between hinges divided by the story height h. So if this L over L sub h is the same at every story, which it may well be, you can cancel it out, and it's just the probable moment of the beam divided by the height. And you can do that for the number of beams at every story. If the number of beams is going to be the same at every story, then that could also cancel out and could be a very simple, calculation. All right, well, we don't have anything designed yet. We think we're going to proportion everything to the demand, and so we don't think we're going to get a weak story. It's not likely, but it's something that we're going to have to check later after we've selected our members. So here are the vertical irregularities. The soft and weak story are things that we feel reasonably sure we're not going to get, but we will check in the end. Okay, next, the load combinations. We have to determine the redundancy factor, the overstrength factor, vertical seismic load effect, and the live load factor. Since our live load is not greater than 100 pounds per square foot, and we don't have public assembly, for the seismic load combinations, we can use a live load factor of 0.5. All right, so the redundancy factor for the moment frames, it tells us the ASCE 7 tells us in table 12.3-3 for a moment frame, you can evaluate it with a beam removed. So we're going to 5 beams instead of 6, and it tells us if we meet the two requirements, not reducing our base shear strength by more than 33% and not triggering an extreme torsional irregularity, then we have a redundant system. There are 2 different ways that we can do this. One is doing an elastic analysis, which is pretty easy. You just take the element out of the beam and rerun the analysis that you're probably already doing for the design of these frames. And then we're also permitted to do a strength analysis, which may show a redundancy factor of 1.0 in cases where the elastic analysis doesn't. So by way of demonstration, we can do the elastic method here. We're down to 2 frames in this direction. we're going to assume that we have equal loading at lines A and D. In other words, that the braced frames aren't really helping us out. So we're going to have, now we remove one of those, and now we have 5 frames working for us. Those 5 frames see essentially a load that's eccentric to their center of rigidity. That eccentricity is 7.5 feet, assuming that we have the same stiffness. Now we're going to assume for that torsional moment that torsional moment is divided between the braced frames and the remaining 5 frames. So there's a torsional moment because the moment frames are separated by a moment arm of 75 feet, and the braced frames are separated by a moment arm of 120 feet. We're going to think the braced frames are going to take a little bit more of that torsional moment, so the moment frames are taking about 40% of the torsional moment. So if we put together the direct shear plus a portion of that torsional shear, we get a 32% increase in force in the frames at line A, which is less than the 33%. So the elastic method works, but just barely. If we wanted to do the, so here's the elastic method, running out all those numbers. And yes, the displacement corresponding to that load compared to the average displacement is a ratio of 1.08, which is a lot less than the 1.4, which would trigger the extreme torsional irregularity. So because we have a very good torsional layout, there's not a lot of twisting, so we're not in danger of that extreme torsional irregularity. Row of 1. If we did the inelastic method, we could simply say all of these frames are taken up to their full strength, so that means only a 17% strength loss. But it's going to have to twist a bit. So now we have an eccentricity still of 7.5 feet because the load is centered on the diaphragm, and these 5 frames create an effective reaction that is centered on them. So there's a torsional moment. That torsional moment, because we're saying we're taking the full strength of each of these frames, they can't take any of that torsional moment, so the torsional moment goes entirely to the braced frames. The braced frames are going to be okay for strength, but the system is going to twist more. So we have a displacement at line A and line D. The displacement at line A and line D is going to be the same, but the displacement at line 1 and line 5 is going to add a little bit of more. So at line 1 and line 5, we have the load that went to the braced frames divided by their stiffness. We're assuming their stiffness is going to be the same as the stiffness of each of the moment frame lines. And so we get a little bit of displacement up at line 1 and down at line 5. And that gives us a total rotation. And that total rotation can contribute to extra displacement, say at line A, and a little bit more. So we can do inelastic methods as well as elastic methods to do the redundancy factor. In the braced frame direction, we remove one brace. However, when we remove one brace, we go from a system that has this stiffness, where the stiffness is related to the cosine cubed of the stiffness of the brace. Remove one brace, then really we have 2 sources of flexibility. We have the flexibility of the brace and the flexibility of the beam, which we haven't designed yet. But if we look at that, that beam flexibility is going to be quite dominant compared to the brace flexibility, and it's going to be a loss of stiffness that's going to be much greater than 50%. So we're going to simply say that we lose 100% of that braced frame. And then with the braces that remain, we have a significant loss of strength and significant loss of stiffness. So we're going to say this is how it's resisted, and all of the torsion goes to the moment frames. Then we've lost a lot of strength and caused a lot of rotation. So that rotation is actually going to be quite large, so that essentially we're pivoting on the braced frame at line 5, and we're not going to be able to justify a redundancy factor of 1.0. So for the braced frames, we're stuck using the redundancy factor of 1.3. And that's not a surprise. We just have 2 braced frames, 1 on each side. It's a reasonable way to design. All right. So here are the overstrength factors that we're using straight out of that table, 12.2-1 from ASC 7. Vertical seismic load effect enters into each of these equations for the load combinations, including seismic, and it enters in as 0.2 times SDS, and so we can plug that in as well. So 0.2 times SDS is 0.2D, so 0.9D plus the vertical seismic load effect becomes 0.7D, 1.2D becomes 1.4D. So the basic load combinations, like this, we have F1 times live, we have 1.2 times D, we have E vertical and E horizontal times rho. For the special moment frame, it's 1.4 including the vertical effect, 0.5 times live, and a redundancy factor of 1, 0.7 for things causing tension. Buckling restrained braced frame, we have the redundancy factor of 1.3. Those are the basic load combinations. The overstrength seismic load combinations, pretty similar, except instead of the redundancy factor, we use the overstrength factor that we get from that table, 12.2-1, and it's a different factor for the BRBF compared to the SMF. And then we have the capacity load combinations. These are load combinations that AISC 341 requires us to use, say, the capacity, in some cases, of the buckling restrained brace to develop the load, say, on the columns. So we're calling those ECL. They're combined with gravity loads where appropriate. And these are the combinations. So ECL would correspond to the yielding of the buckling restrained brace or the yielding of the special moment frame beam, and where appropriate, we combine them with gravity loads using these factors. So these diagrams show you appropriate places for each of these load combinations. These elements here, the moment frame beams, we check them with the basic load combinations, so no amplification factor, no overstrength factor, I should say. The overstrength factor we use for the moment frame columns and for the collector beams. And we use the capacity load combinations for shear in our column splices and shear in our beam to column connections. Similarly, here's the diagram for the buckling restrained braced frame. The braces are sized using the basic load combinations, so with the rho factor but not the omega sub O factor. The collectors with that overstrength factor. And the beams and columns of the braced frame get the capacity load combination, so forces corresponding to yielding of those braces. For drift, this is the load combination that we use. I'm putting in the dead and live load there. The dead and live load don't typically directly cause drift, but they do contribute to the P delta effect. And so that's the appropriate load combination to use for the P delta effect for drift analysis. Remember that the base shear is different for drift compared to the base shear for strength, that we are allowed to use the calculated building period. If you'll remember back, I think, to session 1, the base shear decreases with increasing period, but the seismic displacement increases. If you look at a displacement spectrum, the displacement keeps getting larger with increasing period. So the more flexible your building is in your model, even though the load is dependent on period and goes down, the displacement will go up. All right, so to summarize the work we've done today, we've presented the building that we're going to design, determined the seismic accelerations, determined our seismic design category, selected the moment frame and braced frame systems that we're going to use, calculated our base shear, and set our load combinations up. Additionally, we've determined that we're doing the right thing by sizing these members for seismic and then holding off on the wind design to verify later. So with that, this is the end of session 1. Next week, we will do building analysis and diaphragm design. And then we'll get on after that for the design of moment frames and braced frames. So we finished our work for today, except for answering questions.
All right, Raphael. Thank you very much. We do have some questions from the audience, and the audience can be reminded that if they have any questions for our speaker on today's topics, they can go ahead and submit those via the chat feature. But before we get to those questions, we'll go ahead and actually test the audience with a few questions with a couple of interactive polling questions. And so the audience can feel free to participate by selecting the answer on their own screens that they think is correct. So the first polling question is this: which of the following contain quality requirements applicable to steel structures in seismic design category D? The options are A, AISC 360, Chapter N, B, AISC 341, Chapter J, C, AISC 358, Section 5.7, D, AWSD 1.1, Section 6, and E, AWSD 1.8, Section 7. Or is it all of the above or none of the above? Once again, the question is, which of the following contain quality requirements applicable to steel structures in seismic design category D? Let's hold off a little bit longer, let everybody get their answers in, and we'll go ahead and close the poll. Well, Raphael, it looks like about 3/4 of the audience thinks the correct answer to this one is F. Did they get that one correct?
Yes, they got it correct. So anyone who answered A, B, C, D, or E, you're not totally incorrect because they do contain requirements applicable to seismic design category D, but it's important to note that all of them contain requirements applicable to structures in seismic design category D.
All right, good job. We have one more question for the audience. This one's a true or false. Is it true or false? A building with the center of mass aligned with the center of rigidity cannot have a torsional irregularity. Is that statement true or false? A building with the center of mass aligned with the center of rigidity cannot have a torsional irregularity. All right. The last responses are coming in, and we're going to go ahead and close the poll. All right, so this one's a little bit of a split decision. We have about 2/3 who think that statement is false and 1/3 who thinks that statement is true. Which is the correct answer, Raphael?
So the statement is false, although it's not very common. If you have a building with all of the lateral resistance right in the center, aligned with the center of rigidity, you still can have a pretty big torsional problem, and that's the reason we have the accidental torsion in our building codes, to pick up on that lack of torsional resistance for such structures.
All right. With that, we'll go ahead and move this into a question and answer session, and we have a few audience questions here. And the first one will take us to slide 38. And the question is simply, can you explain the CVN toughness that is indicated on these slides?
Yes, so for example, on this slide, where we have a plate material with thicker than 2 inches, if you go to AISC 341, section A33, it says where you use such material as part of your seismic load resisting system, you should require it to have a sharp EV notch toughness of 20 foot-pounds at 70 degrees. So the reason that we like the toughness is that it will slow down and prevent crack propagation, which can preserve the integrity of the seismic system under the multiple large cycles of seismic loading. Now, the reason we have a threshold of 2 inches has to do with observed material toughness from multiple tests. That the thinner material tends to have high toughness, and low toughness material seems only to crop up for these thicker elements. So we only ask for the testing for the thicker elements because we're pretty confident we'll get that toughness without spending effort on testing for the thinner elements.
All right. Our next question brings us to slide 51, and this question isn't specifically about this, but this audience member is sort of anticipating the analysis of the system. And his question is, how can we model the connections for the gravity framing?
Yeah, that's a good question. So for a moment frame such as this, if you're relying on the beam to column connection to provide your resistance to lateral loads, that really should be a special moment frame connection. So generally, the beam to column gravity connections are modeled as pinned. Often, as well, to ensure that the moment frame is designed for 100% of the load, engineers will model the gravity columns pinned top and bottom, so all of the shear goes to the moment frame, and that's designed for 100%. I think that's probably the most typical way of doing it. Engineers used to doing a nonlinear analysis or ASE 41 analyses sometimes spend more time or sometimes are more comfortable analyzing the frame that's actually there with the behaviors of each of those elements. But if you want to evaluate the beam to column gravity connection for moments and rotations that are imposed, I think the work of the designer gets a lot more. So typically the beam to column gravity connections are modeled as pinned.
All right. Our next question is slide 54. could you explain what is the 1.4 factor shown for the brace stiffness here?
All right, so we'll get, I think we did have that in one of the recorded sessions, and we'll come back to this in both next week and in session 4. When we size these braces, we determine a required area. Let's say the required area is 5 square inches. If you have an analysis model, either by a hand model or a computer model, and you have a 5 square inch element going from work point to work point, that has a certain stiffness associated with it, AE over L. Now, the actual brace that you're going to put in there is 5 square inches over a certain length of it, but outside of that length, the effective area of the brace is much larger. So it's a non-prismatic element. So if your model has a prismatic element of 5 square inches, the right stiffness to put for that prismatic element is approximately 1.4 times that 5 square inches, just to reflect the non-prismatic nature of the brace. Now, that 1.4 is appropriate for this particular condition that we're considering. For longer braces, say if you're doing a convention center and your braces aren't 20 feet long, but they're 40 feet long, that factor is probably closer to 1.2 or in that region. Or if you're using a very short brace or other conditions, it might be as high as 1.6 or 1.7. So that's why we're saying consult with the manufacturer or look at the literature. It's a function of the brace length and the force that's being transferred.
All right. Our next question is getting into this irregularity portion of the presentation, and it was specifically on slides 86 and 87. So the question is, could you explain a little bit more? If we have more or less than 0.7 the stiffness compared to the next story, is it correct or not? So are we looking to have less or more stiffness than this 0.7 limit of the story above?
Right. So if you have, if the story above, the blue arrows there, give us a stiffness essentially of effectively, say, 100 kips per inch. If we are at 70 kips per inch at the second floor, the red arrows, then we don't have the irregularity. But if we are 69 or 60 kips per inch at the red level, then we do have that irregularity. So the threshold is 70%. You can be a little bit softer than the level above, but if you're more than 30% softer, then there's going to be a dynamic effect that the code asks you to address via the dynamic analysis.
All right. Our next question is on slide 117. And the question is why is the overstrength factor applied on the column designs?
Why is the overstrength factor applied on the column designs? Okay, so this is a moment frame. Probably at lines 2 and 3, the overturning, the seismic axial force is going to be quite small. But at lines 1 and 4, that's where the overturning of the moment frame is going to be delivered, right? Each of those beams is going to have moments at each end, and therefore it's going to have shear at each end. And at line 1, let's say all of those shears are pulling that column up, and so there's going to be tension on that base plate. And at line 4, all of those shears are pushing the column down, so there will be compression on that base plate. So in order to make sure the column has adequate strength for the combination of, say, that compression plus the flexure associated with the moment frame behavior, we use the amplified load because we expect each of those beams to yield and strain harden and to develop forces that are much larger than the base shear forces that they were designed for.
Okay. And one final question, and it happens to also be on this slide. This will be our last question we get to. Do you design the base plate, anchor bolts, and connection and foundation with the amplified forces from the columns?
Okay, so the requirement at the base does invoke the amplified seismic load. So the question was the base plate, the anchor rods, and I'm sorry, what else?
And the foundation was the third one.
And the foundation.
Specifically mentioned. Yep.
Yeah, so the foundation is not required to be designed for those amplified loads, but the base plate and anchor rods are. So you have to use a bit of judgment in proportioning those base plate connections. I think I have a method that I think is consistent with both the written requirements and the intent of the seismic provisions when it comes to the design of those base plate connections. And the good news is we're going to get into that in great detail in session 4. There may be other interpretations that are consistent with the requirements of the AISE 341, but we're going to do my interpretation in this class, and you feel free to follow that interpretation or develop your own. But at least we'll cover how it meets the requirement.
Thank you to Rafael Sabelli for presenting today, and thank you all for your participation.